recording.
Invite Aaron
On Zoom
Robertson,
on
talking
Zoom.
about trudging through the two large.
So we can move the tripod. Microsoft.
Give everybody a moment to have a seat. So I was a student of Doron's when he was at Temple University. And something he probably doesn't know is that before I took his class, I was planning on either leaving grad school or at least leaving Temple. I had retaken the GREs to make myself more mobile. So it's not a stretch to say that I probably wouldn't be a mathematician if it weren't for Doron. So this is
a good thing or bad thing?
Don't know. Based on what I'm going to present today, a bad thing. So this is my opportunity to thank him for that. So what I'm going to show today are, as the abstract reads, no theorems, no proofs, just what I've been doing for the past 3 months. If you've seen my Facebook page, I've had a brick wall with an X on it that says hit head here. That's what it feels like I've been doing. So what I'm working on is called the too large conjecture. So this is in the general field of Ramsey theory. And I also, back when Doron gave me a problem, he gave me a different problem than what his other students were working on in WZ, a permutation pattern kind of stuff. He gave me a Ramsey theory problem. And he knew better than I did that that's kind of really the type of combinatorics I like. And so this is in that area. So first I need to just take an arbitrary set D of positive integers, and we call a k-term AP arithmetic regression. A D AP if we have A plus D, A plus K minus 1D with little d in the set. So, what the too large conjecture says is if for any two coloring of the positive integers, so any partition into two sets, we have arbitrarily long monochromatic DAPs. So we have arbitrarily long, so as long as you want, arithmetic regressions with common difference from the set. Then we have such a result for any finite color. So if it works for two colors, it works for any number of colors. That's the conjecture. If you look at one of the proofs of van der Waerden's theorem on arithmetic regressions, this is how you get the full theorem. You work on two colors, and then and then you can go to many. And so it's a natural question to ask: what if I restrict the gaps, the common differences? So if D works, and by that I mean satisfies this statement for R colors, then we'll write D is in L sub R, and it's called R large. Yes. Darker?
Yeah.
So, is that better? Okay. So this is called R large. So, the two large conjecture is this. If it works for two colors, it works for any finite number. And this statement is just called large. Okay, so there are several ways that Van der Waals theorem is proved. So I'm going to look at all those different ways and see how we can try to attack this problem. So the first just straight combinatorics. You can use a forcing argument, or you can use induction, double induction, to do this. You can look at those. There's no easy way to modify it to get this. So you can try that. Then you can look at Semerades theorem, which says, so first I need definition. The upper density of A is the lim sup of A intersect that. So the upper density, the density may not exist, but if you have just the set A, you look at the lim sup, we have this. Semerades theorem says if the upper density is positive, then A has arbitrarily long arithmetic regressions. And so from here we have, if you do a finite coloring, pigeonhole principle says that one of those color classes has to have positive upper density. Van der Waals theorem holds. So you go and you look at Semerades' paper, and everything you've read says this is a difficult and deep paper. This is from the paper itself. It was apparently enough steps that he put this in the paper as a sketch of the flow chart of the proof. And it uses Van der Waals theorem to actually prove it. So now we got a problem because Van der Waals theorem itself didn't really shed any light on this. And if you follow the proof here, you'll see that he needs the common difference. He gets one common difference, D1. He gets another one, D2. And at some point he needs to add them together to get a common difference of D1 plus D2. But our arbitrary set doesn't have any structure. It's just arbitrary. So you go through the proof enough to realize that's not going to work, at least not easily. Okay, so then Furstenberg comes along and gives an ergodic proof. And then this is related to topological, so I'm going to get these side by side. So topological says, let's let xt be a minimal dynamic system. T is a homeomorphism. X is the space. So if we have a minimal dynamical system, minimal in the sense that there is no non-trivial closed invariant subset. So if we have minimal dynamical system here, for any open set U in the space, there exists and n